Okay, we are happy to have here Markus Heyl. Okay, and so Markus, you have 1 hour and a half, and you have just to. I mean, some of the students directly ask you question. If they ask you on the chat, we will stop you and ask the question. So you just have don't bother about the chat. Okay, you can start when you want.
Thanks a lot. So let me first quickly set up my environment here.
Sorry, Markus, you are mute.
Sorry. Thanks a lot for unmuting me. Yeah, sorry, I just wanted to say I need 1 second to set up everything. Not now. Done. Okay, good. I think you should now see both like the text that I've been writing on my tablet and also like myself, I guess. Good. So welcome everyone. Good morning to this last lecture of the school, which I guess was, as schools are like always, a bit exhausting. So I decided to keep everything very lightweight in what I wanted to tell you, and in particular, I also would like to make 2 breaks, like each after like 30 minutes, so like that you can grab a cup of coffee and like just relax for a few minutes until we continue. So overall, the topic you can see again up here, it's on disorder-free localization in lattice gauge theories, and these might be all terms which you don't know yet. At least I assume that many of you don't know about disorder-free localization, and also not so many about gauge theories. But I can tell you that in the end, you don't need any prior knowledge on any of these things, just quantum mechanics. Quantum mechanics 1, and that's it. And with this will be perfectly sufficient to guide you through all I wanted to tell you. So overall, there is also a plan, like for the lecture, but honestly, I can always adapt and modify according to how things go. And so please, therefore, always feel free to ask questions, interrupt me if you would like to clarify something, if whatever. So there's we have plenty of time for the things I want to tell you, and then I can always adapt and change my own schedule, so to speak. Exactly. So with this, let me start now my actual lecture, and like let me first somewhat motivate why I think the topic that I would like to present to you is very interesting and also very promising for the future. So on the one hand, one of the 2 things that are contained, or topics which are contained in the title, is gauge theories. Now, why should one consider gauge theories? In the end, they are extremely important classes of models. They play an interdisciplinary and fundamental role in physics. And importantly, like across different fields of physics, like ranging from, say, high energy physics to strongly correlated quantum matter, topological systems, frustrated quantum magnets, but also a lot recently to the context of quantum technologies, or like quantum simulation and things like that, or like quantum computing even. So like overall, this is just to say like gauge theories in the end, if you look closely, are almost everywhere. So that certainly motivates us to say, like, to anticipates that gauge theories are an important class of theories. And the second aspect of my title contains like localization, or this sort of relocalization in particular. What that refers to in the end is to the fact that there can be potentially some non-ergodic behavior. And so why is non-ergodicity in the end an interesting aspect of quantum many-body systems? So on the one hand, of course, like these systems don't behave as one would generically expect dynamically, meaning that they don't equilibrate to a thermal state if you let them evolve on their own. So that by itself has like important implications for statistical physics, thermodynamics. But personally, I favor one aspect much more, and which is that that has been very much realized within the last 10 years, particularly in the context of many-body localization, which is that if you have a system which is non-ergodic, what you can get is that you don't like you relax some constraints that you always have in equilibrium systems. And what this allows you to do is to generate new quantum phases, new phases of matter, which would not be possible in any equilibrium context. And the most prominent example of this is probably the discrete time crystal, but there are many others. And now that's somewhat the main big implication of why I think that the topic I would like to discuss with you is a promising one for the future, is that it combines two things. On the one hand, like gauge theories, which share their own like importance in many-body physics, and non-ergodicity, non-ergodic behavior on the other side. And I would like to discuss with you why these two things are related to each other. And so the outline of my talk you can see here. First, I would like to tell you how you can think about lattice gauge theories, and I will not give you a very detailed introduction, but just to outline those aspects which will be important for what I will discuss later on, and that will be actually rather simple. So you don't have to know anything about gauge theories to understand this. In this, like, and in particular, I would like to emphasize and work out the implications of one defining property of gauge theories, which is that they have local symmetries. And local or like symmetries generally, you know that according to Noether theorem, that this leads to conserved charges. And I would like to, in particular, discuss the implications of such conserved charges onto the dynamics of gauge theories. And I would like to show, that's like part of the second point 2 here, that I would like to show you that this leads to something which one calls Hilbert space fragmentation. In the next step, I we'll give you a very simple model of QED on a lattice and discuss again the local symmetries, namely which are somewhat related also to Gauss' law that you well know from electrodynamics. And afterwards, I will introduce one particular model, a class of model which is relatively simple and which allows us to more concretely discuss dynamics and gauge theories. And finally, I will introduce to you the actual concept of this sort of relocalization. And then, if time permits, I can go on. I should not say forever, as Markus Heyl was pointing out, but I can still go on for a while if you wish. Okay. So, any questions up to here, or just continue? No one objects. I will then start with my first point and introduce to you what elementary aspects of lattice gauge theories that will be important for later on. Okay, so Point 1, lattice gauge theories. I will, in the following, abbreviate them with LGT, but I don't have to write so much. In a nutshell. Okay. So, how should we think about gauge theories? Let's just take let's just look at an example. I think that's probably the easiest thing that to do at this point. So lattice gauge theories are quantum systems on some lattice. And so we have lattice sites. These are the blue dots here. That's like one half of the story. And so we have these lattice sites, and in gauge theories, we, in addition to having degrees of freedom on lattice sites, we also have degrees of freedom sitting on the links. We when considering the lattice sites, that's where some degrees of freedom are living, and we call these degrees of freedom matter fields. In the context of quantum electrodynamics, we will come to that later, quantum electrodynamics on a lattice, these matter fields will be electrons and positrons. And then we have these degrees of freedom which sit here on the link, and this is where we have now our gauge fields. And in the context of quantum electrodynamics, these will be the photon. Like this will be a bosonic degree of freedom that sits there on a link. Now, generally speaking, as I said, like these gauge fields, you can typically think about like being either spins or bosons, like the photon, QED. Photon would be like the example of a boson, of course. And the matter fields, these are typically these can be various different species. These can be fermions or fermions in the context of, say, electrons, positrons, but these can also be bosons or can also be spins in the end. You can put everything there. So the example I was just mentioning, so when you consider QED, then we would have fermions coupled to bosons. Oops. Wait. Boson.
Markus, we have a question.
Yes, please.
Yeah, so I just wanted to ask, so even the gauge fields are defined on like discrete lattice, like some Z or something?
Sorry, can you say it again?
So is the gauge field also defined on discrete lattice, like the matter fields here, or like there are...
Did I understand correctly that you were asking about discrete lattice here?
Yeah.
Uh-huh. So in the end, what I do here, I put a gauge theory indeed on a lattice. So this is not, I will not consider gauge theories in the continuum, which would be also something that one could look at. Just for the sake of what I will discuss later on, I will only consider putting them on the lattice. So you can think of here, maybe that clarifies it, but if not, please ask me again. So that for the case of putting QED on a lattice, we would have here on these links between lattice sites, we would have that there is one bosonic degree of freedom which sits there locally and which can move around and maybe effectively hop from here to there, say. Is that addressing your question?
Yeah, so essentially, if I'm thinking about it correctly, so like, you know, there is a Z lattice and where the matter field sits, and there is a different Z lattice where the gauge field sits, and then somehow they can interact. Is that the correct
Exactly,
picture?
exactly. That's it. Exactly. Okay. So now, so like in the end, you can think of it in various different ways. The way I I will use it throughout the lecture, is that overall, like a lattice gauge theory, you can think of like a lattice with lattice sides, the blue dots, and like and with further degrees of freedom which sit on the links between two lattice sides. Alternatively, you can think of like a lattice with like all of these being lattice sides, and say the even lattice sides being the matter fields and the odd lattice sides the gauge fields, as you wish. And of course, like we then need also like a Hamiltonian, which then describes how like these degrees of freedom couple. This will be I will do later on.
Cool, thanks, sir. Yes, it's clear. Yeah.
Welcome. So please always interrupt me. We have time. Okay. So let me just outline that. Finally, like the fermions here for QED, these will be electrons and positrons. And we come to that actually as a concrete example later on quite a few times. So like these are the photons. So like this is just to give you an idea what the real space structure of a lattice gauge theory looks like, and that's like of this type. But I've not yet discussed any physical property. And now let me outline the most important one for the following, which is that lattice gauge theories always have a constraint. And that constraint is that they have a local symmetry. And this will be super essential for what I will discuss later on. So what is a local symmetry? Or what does it mean to have a symmetry? I guess that's something you also somewhat know from either classical mechanics or quantum mechanics. In the end, on a Hamiltonian level, it means some invariance under a local transformation. So any symmetry is always like any symmetry is associated to a transformation, and like the physics or like a symmetry in the end means that applying this transformation doesn't change the physics of your model. So that a local symmetry in the end implies that the physical properties are invariant under local transformation. Yes, so what does that mean practically? So it means that for each lattice side L, let me specify that also, like again here, what I mean by L. So what I will do, I will label lattice sides only for the matter fields. So like this will be, say, lattice side L. Then we would have lattice side L plus 1, L plus 2, L minus 1. Okay, this is what I mean by L. Now the local symmetry means that for each lattice side L, there is an operator GL which has the following property, namely that it commutes with the Hamiltonian. So like that's to some extent the essential definition of local symmetry, or like that's the general property of a local symmetry that I will use in the, or will be important for the following. So in the end, for those which would like to know a bit more, let me just say that these GLs in the end are the generators of this local transformation, of this local symmetry transformation. But in the end, it's like actually not crucial to understand this. You just have to know there is for each lattice side there's an operator which commutes with the Hamiltonian. And we will see some very concrete examples like that. You will automatically understand why such like operators should exist that commute with the Hamiltonian. Now we have to distinguish two different types of gauge theories. And this is as follows. So on the one hand, there are gauge theories which are abelian. And so now we have, and what do they, what does that mean? So in the end, we have for each lattice side this property above here. Now this means we have various of these operators GL that commute with the Hamiltonian. And now there's one class of gauge theories for which also like all these generators GL also commute mutually with themselves. That's called an abelian gauge theory, and QED, for instance, is abelian, quantum electrodynamics. Whereas like QCD, say like quantum chromodynamics, that's certainly not abelian, that's a non-abelian gauge theory. And you somewhat can maybe take this as a message, like QED
we have a question.
is very difficult. Yeah, please, question?
Emal, first.
There are matter fields and gauge fields. Gauge fields live on links, and the matter fields live on sites. And here, your gauge generators act only on sites. It doesn't touch links.
No, good question. So like I will label these generators by lattice sites, but they will include both matter and gauge degrees of freedom. So let me give an example to clarify that, but we will come to that. So in case of QED, this GL will be nothing like a discrete version of like lattice divergence of the electric field minus the density. And so it will involve a density, charge density at a given lattice site. So this here are matter fields. That's the charges, like that's electrons and positrons, and that's the gauge field, the gauge, or like the electric field. Sorry, like not the gauge field. It involves the electric field, the gauge degrees of freedom on the link.
Okay. So look, your matter fields and the gauge fields, they interact, and your gauge symmetry should somehow encode this interaction. Am I right?
Exactly. You will see that exactly. So I've not yet shown you any model how that interaction will look like, but so the interaction has to be such, like if you were to write down any version of QED whatsoever, we know that Gauss' law should always hold. That's Gauss, like in the sense that this operator should commute with the Hamiltonian, and now like QED therefore only allows for certain types of interactions, namely only those which commute with this operator, and we will see one of these later on.
Okay, thank you.
Was there another question?
Yeah, no, I guess it was basically the same question, because I was wondering, the problem is what I was used to see in, for example, SUN gauge symmetries is that the commutator is non-zero, not because the operators do not commute on different positions, but because of the different components of the group on the same side.
Yeah, like there can be now various different levels of complexity here. Let me directly emphasize, like I will only consider for simplicity the case of abelian gauge theories. Like that's what we will what we will consider. And not the case of, like, that's the other example, like non-abelian gauge theories, which are which are much more difficult to study.
Okay.
But like that, some further question from your side? Or all clear? Okay, good.
There's one by
Like-
Saptarshi, which is related, but probably. So the GL includes also meta sites and the associated links to it. No? So the index.
Exactly. Exactly. So that's like the gauge degrees of freedom on the links nearby, and that's like the matter sites. But we will see a concrete example later on how this looks like. Okay, good. So, but for the moment, we don't need these details like how a Hamiltonian looks like. So, what I first would like to discuss are some very general implications of local gauge symmetry, in particular when the gauge theory is like the model is represents an abelian gauge theory. And the most important implication is in the Noether's theorem, which relates symmetries to conserved charges. And as I was outlining, I would like to show you how this leads to a phenomenon which is now very well, rather widely studied in broad classes of models. And this is the property of Hilbert space fragmentation. And I would like to tell you what that is about. I'm sorry for this one guy always sending me messages. I hope he will stop at some point. Good. Yes. So from Noether theorem, we know that symmetries are also always implying conserved charges. Now, therefore, like having, say, having a local symmetry, like that was in the end given through these generators GL and that they commute with the Hamiltonian. A local symmetry implies in the end that we have a local conservation law. And like that's like almost trivial here to see, but it has actually huge implications. And local conservation law just means one way of viewing this is that if you study the time dependence in the Heisenberg picture of like this generator GL, which is just the following here, that as the G commutes with the Hamiltonian, like it's actually a constant of motion, right? There's no, that's rather straightforward to see. So
we have a question by Saptarshi. Is there any global symmetry in such systems or only local symmetry?
So you can also have global symmetries and actually also like large, like sometimes you can also have that there are some large gauge transformations where involving like fractions of the system, or some symmetries involving fractions of a system, which are like not like purely local. You can have everything, like the depends on the details of your model. But what is certain is that you always have these local symmetries.
Okay.
But you can also have more.
Thank you. Thank you.
Okay, now, so like that's almost trivial to see here, but it, as I said, it actually has important implications. Now, considering first, like again for a moment, abelian lattice gauge theories, what we have is that all these conservation laws, as the GLs commute with each other, are also like independent of each other. and they commute with each other, obviously. So the upshot of this is that there is overall an extensive number of conservation laws. Because for each lattice site, you have such a conservation law. So extensive meaning in the thermodynamic sense that this is proportional to system size. And those which are familiar with integrability or the question of
we have another question. Can we also
please, yeah.
go the
Please go
other
ahead.
way around? Does an extensive number of local conserved quantities imply an underlying lattice gauge theory?
So you mean whether it also holds the other way around, that an
Yes.
extensive number of conservation laws? No, this is not the case, because you can have, that's actually something I wanted to mention just now, is that there's another class of systems which has an extensive number of conservation laws. But these ones are not gauge theories. These are just so-called integrable models.
Mhm.
I guess you have heard this notion already during the school. Systems which are in some sense exactly solvable and have therefore also a large number of conservation laws and dynamical constraints. So the other way around is not
Okay.
one cannot argue the other way around.
Okay.
Okay?
Yes.
Perfect. Yeah, so already here you can see, so I just wanted to point that out. I said that now that there is this other class of non-ergodic systems which are called integrable, which have an extensive number of conservation laws and which are integrable because of an extensive number of conservation laws. So which already here might indicate, there can be something about these gauge theories now on a fundamental level, that they have that they might have very different dynamics from a generic interacting quantum many-body system. And all we used up to now was nothing very specific. We just used that there is a local symmetry. Now I think let me do what I promised. Let's do say a 3-minute break to refresh everyone. And I'll continue now at 9:40. I think that's a good point to make a short break. But please, if you have further questions, keep asking. I have time.
I have one. So I didn't get if lattice gauge theories may be intended as a particular case of integrable system in this.
So the point is that there is an extensive number of conservation laws, but extensive just means proportional to system size and not equal to system size.
Okay.
And the reason is very simple. So we have one conservation law for each lattice site, but this doesn't mean for each degree of freedom, because we have lattice sites are only half of the degrees of freedom, because we also have the gauge degrees of freedom on the link.
Okay.
So somewhat half of the degrees of freedom in the system are dynamically blocked due to conservation laws, roughly speaking. And the other half is still free to move, in principle.
Okay.
In an integrable system, you would have that the number of conservation laws is equal to the number of degrees of freedom. Here it's just half.
Mm-hmm. And so just one other curiosity, and maybe these you're going to discuss later, about if one would like to compute for this kind of system, level statistics, and what one is expected to find.
What I will show you, or try to argue, I will not show you any concrete data, but what I would like to discuss with you is that in the end, that you can have both, you can get, depending on the model and some details, you can get either Wigner-Dyson or Poisson. So
Nice.
in that sense, that's exactly what this disorder free localization is about, that there can be instances of gauge theories where, although they're interacting, so like they're not free particles, they're interacting, and just because of gauge symmetry, they obey Poisson statistics, level spacing statistics.
Okay, thank you.
And I should say like one example, but that's like something I will probably not discuss just because of time reasons, but just that I mention it. Like there's a version of like a simple version of QED in 2 dimensions, where, for instance, you find this Poisson level spacing statistic.
Okay, very cool. Thank you.
Welcome.
I had another question about the point that Saptashi, I think Dominic mentioned that. So can you argue in this way? Suppose you have extensive degrees of freedom, then it's either a gauge theory or an integrable systems, or there can be other classes also.
Good question. Let me put it that way. I'm not aware of of another class of models which has this extensive number of degrees of freedom. Or like, so, like I would say that 3. So like integrable systems, then many body localized systems, which are like, which have this extensive number of local integrals of motion due to strong disorder, gauge theories. That doesn't mean that there are maybe not more, but I don't know of any. Okay. Like to the best of my knowledge, there are only these 3 classes of systems which can have these local integrals of motion.
And I had another question about the gauge part of it. So usually when you have a gauge symmetry, usually that means you have unphysical degrees of freedom. I mean, at least that seems from the tensor network system. Where are the unphysical degrees here, and you have to trace out.
That's actually a good point. So to some extent, when I understand like these things appropriately, then it's exactly that especially when you come from a high energy physics background, that you need gauge symmetry essentially to project onto a physical sector, to project out some degrees of freedom.
Yeah.
And we will somewhat come to that later on. Here, in the condensed matter context or quantum many-body context, the philosophy is different because gauge theories are somewhat like emergent effective theories of, say, a frustrated magnet.
Okay.
And so there, it's not always about projecting out degrees of freedom. They are just like the effective descriptions, like they emerge in the end. But actually, this question has a lot to do with some aspects I wanted to discuss later on, and in the context of so-called super selection sectors. If I'm done with my explanations on super selection sectors and I've not addressed your question, please ask again. Okay, I think that's the perfect point to discuss this.
Thanks.
Sorry, actually, I had a question. So yeah, so if I understand properly, so like QED problems are being mapped onto this kind of like lattice gauge theories, and like they can be understood from there. So like, okay, like what I was thinking, that why do we do it like this, that okay, that there are matter fields on sides and then gauge fields on the like links. I mean, why don't we see it in this way, that okay, that we are attaching some sort of bath to each of the lattice sides? Like,
yes, I think that's mainly a matter of like convention also that has been chosen in this context. You could, of course, like I'm sketching this briefly here. Of course, you could also, and that would be no problem. And maybe so. I think you can easily deform, like say, this kind of real space structure to something which is like saying that on each lattice side you have now 2 degrees of freedom which live there. I think like that's certainly also a possibility. like you can always map like this here to that one on the right hand side, but it's just a convention to use a representation of this form. And it also, like, to some extent, so where this representation also helps, and that's probably also like one of the reasons why these representation is chosen, is that when you want to do a continuum limit, sending like lattice constant to 0, then this representation is actually better suited than this one. We will not be interested in taking the continuum limit, so it doesn't matter. But if you are interested in the end in a continuum limit, then you anyway should use this representation.
Right, because yeah, I think like in this representation, the original representation, you have something like some link operators, which like in 2 dimension looks like a cross, and then you have like a square operator sort of things.
Yeah, you're right. Actually, in 2 dimensions, like this mapping here, one can do easily probably in 1 dimension. In 2 dimensions, it's becoming more tricky maybe how to actually. So I think in 2 dimensions, you can probably still do that, but the interactions in your Hamiltonian you will get are probably extremely difficult and appear rather non-local. So I think it's just convenient, and that's the convention to use this representation here.
Okay, thank you.
Good. Another question? If not, then I will maybe continue here. So now, what I discussed right now was like the essentially the consequence of Noether theorem that symmetries lead to conserved charges, and in the presence of like in the case of a Abelian gauge theory is that we have an extensive number of conservation laws, which are all independent of each other in the case of an Abelian gauge theory, because all these GLs also mutually commute with each other. And now we use just elementary quantum mechanics, which you well know. And this might remind you also like to the angular momentum operator. So when we have a lot of commuting operators, or operators which commute with the Hamiltonian, so again we have the LH equals 0, and also like all the operators commute mutually with each other. This implies that the eigenstates of H can be labeled by the eigenvalues of all these operators G that commute with the Hamiltonian. GL, right? And that's what you use in the when considering the angular momentum operator, say. So what we will do is we will now introduce like eigenstates of these operators G. So, and acting on some states psi, which are now parametrized by a set of values Q alpha, which are supposed to be the eigenvalues of these generators GL. So these psi are the eigenstates with eigenvalues QL, and now since all the operators commute with each other, we can find eigenstates of all we can find states which are eigenstates for all these GLs. Yeah, and so we have to specify for those states like the set of all these eigenvalues Q alpha that appear for all possible for all lattice sites for all these generators GL. And now the Hilbert space corresponding to one of these sets Q alpha is called a super selection sector. And that will play a very important role in what I will discuss later on. So what it means is that in the end, so the statement that the eigenstates of H can be labeled by the eigenvalues of GL means that if I can find such states psi, which are eigenstates of the generators GL, and which have the property that when taking states of two different sectors, so where the eigenvalues of corresponding to these GLs differ on the left and right hand side, that this is always vanishing whenever Q alpha is different from Q prime alpha. This implies that the Hamiltonian in the end, that's like just a consequence of the local gauge symmetry, that the Hamiltonian decomposes into blocks which are disconnected, and these blocks are determined by these by the super selection sector, by choosing these eigenvalues Q alpha for these generators. And all the other entries of the Hamiltonian are zero. Okay. And that's exactly what Hilbert space fragmentation is about. So that the Hamiltonian decomposes into many small blocks which are disconnected from each other. And here it follows naturally just because of gauge symmetry. Let me notice here, like, for having, like, that's a point where the abelian character becomes important. So if you have a non-abelian gauge theory, things would be a bit more difficult. So the fact that you immediately get this decomposition into like these blocks is like a consequence of the abelian character that we assume here, that everything commutes with each other, and that immediately gives you the blocks. And now, like, that was all very formal. I would now suggest to put in back some physics, but maybe like to assign to all of these things like super selection sectors and these numbers Q alpha some physical meaning. But before I continue there, are there some questions concerning the last part here?
So I had a small point. So are all these blocks because of the GL symmetries, like, are these going to be the same size? Like,
no, they have in general can have different size. And now coming back to one of the questions that someone asked, now the point in the end will be that some of these blocks will have Poisson and some others might have Wiener-Dyson level spacing statistics. And in, say, 20 minutes, you will understand why physically. At the moment, it's just like a very general statement. Later, you will hopefully understand the physics behind this property.
good.
And sorry, I also had a question.
Sure, please.
I mean, for instance, in QED also, you would have bosons, right? So then there would still be an infinite size basically, or not for each block in some sense.
Yes, right. So somewhat implicitly without saying that so directly here, I'm somewhat assuming a quantum model with a finite Hilbert space, so that not really QED where there are bosons, but rather replacing bosons by spin degrees of freedom, as I will do later on.
Okay.
As it's like common models, common gauge theories, especially in the quantum many-body context. But you're right, if you were to do real QED, things would be a bit more subtle here. But let's assume that we have Hamiltonians with a finite Hilbert space.
Okay, thanks.
Thanks for clarifying that.
There's
Good.
one more question in the
Yeah,
chat.
please.
Does the psi labeled by a particular set of alpha make a complete basis of the Hilbert space, I think, of the supersession sector?
So, yeah, you can. So, like the point is, you can find a basis which so you can construct a basis which are eigenstates of these GLs. So like and like these are these psis, but for a like this, it doesn't mean that for each set of Q alphas there's only just one state which corresponds, or one eigenstate. There can be degeneracies, and that's exactly what gives rise to the non-zero size of the blocks that you have here. So if there would be no degeneracies and all eigenstates of the of these generators GL would be there would be no degeneracies, then these blocks would always be of size 1. But if there are degeneracies, multiplicities, then the size of these blocks can be larger. And actually, for a quantum many-body system, these blocks are still exponentially large in system size.
So maybe because I was the one who placed the question, so that means that these super selection sectors are smaller than the number of eigenstates that you have for each generator, let's say. Or...
Exactly. So it's like exactly. So so you can say you will say that you can maybe visualize yourself like why this happens is say you have a charge Q alpha for each lattice side, which can take the value 0 or 1. Let's hypothetically consider such a system. Then this would mean that this set is like has 2 to the L different or like there can be 2 to the L different sets Q alpha, strings of zeros and ones, right?
Yes.
So this means that you will find 2 to the L sectors in your system, which are like decoupled from each other, 2 to the L super selection sectors.
Yes.
Now, depending on your actual Hilbert space, this means, like roughly speaking, that the full Hilbert space size divided by 2 to the L is the typical size of your super selection sector.
Yes.
Yeah, roughly.
Okay. Thank you.
And that, yeah, please.
No, that is clear, I think. Yes.
Okay. Great. And already this one can make use here computationally, and that has been done, for instance, by one of the organizers here, by Fabien Allais. Because for exact diagonalization, that's actually very good to have symmetries which can decrease the size of blocks in your Hamiltonian, because each of these blocks you can now diagonalize separately. You don't have to diagonalize the full matrix, and that helps a lot computationally, and like Fabien Allais has done some very nice work on two-dimensional lattice gauge theories, where he has exactly made use of this property. Good. I see. I have a very a lot of things that I want to say to you. Let me let me give 1 second to think how to proceed. Yes, I will do this. And okay, good. So now let's consider. Now let's go to the physics as I was explaining. Now this was very formal. There was not much physical intuition behind that. Now let's go to the physics. And let's try to visualize what these superselection sectors actually mean, and what the gauge symmetry actually means, and to get somewhat a feeling of what this locus symmetry is supposed to look like. Now, for that purpose, we will look at like a very simple version of QED. Like we again put it on a line, on a one-dimensional line. So we have again our meta sites, right? We have our gauge field degrees of freedom, which sit on the links. And now I will use a certain convention which is often used in the gauge theory context. I will tell you what it exactly means, namely the so-called staggered fermion formulation. Which has been outlined in particular by Kogut, Susskind, PRD from 1975. And within the staggered fermion formulation, so if we have, okay, let me start in this way. In QED, you would describe the coupling between phonons and some charged particles as electrons, such as electrons and positrons. So now you have two types of particles, and it turns out, and that has been shown by Kogut and Susskind, that if you put QED on a lattice, you can do this such that in such a way that you are still dealing with a single fermion degree of freedom on each lattice site, a single fermion, although you have two types of particles, namely electrons and positrons. And you do it in the way that you associate, say, all the even lattice sites to like electrons, and all the odd lattice sites, those and those here, for instance, to positrons. So that's the first step, like that you somewhat double your lattice, the number of lattice sites, but you keep still like 1 degree of freedom on a given lattice site. And you can also see the word staggering here. And so which means that there's also like some kind of staggering involved here, and this goes as follows. Now let me write down the bare vacuum of the theory, so without any particles. So then I would say like this would be a zero occupation. On say like on this lattice site here, that would correspond to that there is no electron. If on odd lattice sites I have a particle sitting there in occupation, this means that there is no positron. If I have, again, a zero on the next even lattice site, that means that there is no electron, positron, and so on and so forth. Like that's why this is called staggering, and there are reasons for taking such a kind of bit of a maybe strange kind of way of writing down things, but there are reasons to do it like that. And So like what I want to say is like taking an occupation of 0, 1, 0, 1 here means that the system is really empty. There are no electrons and no positrons there. And since we are dealing with the empty theory, there are no charges. We would, of course, also not, we won't have any electric field in our system, of course. So I'm also putting here 0 for the electric field everywhere. Okay? So that's the vacuum. There's nothing in there. No electrons, no positrons, no electric field. But of course, you know already from various sources, I guess, that there is nothing like a really bare vacuum. You will have always fluctuations of particle Hall pairs out of the vacuum, and the creation of here electron-positron pairs, like these are particles and antiparticles. So let's do it. Let's make let's create a particle-antiparticle pair, and let's see what such a fluctuation does to the system. So let me do it, say, by looking on this link here, or like these two lattice sites. Okay, so let's create an electron-positron pair. So we have our two lattice sites, which have been initially empty. So we would have a, or like, no, I'm choosing those here, like, where the first lattice site has something to do with the electrons and the second one with the positrons. Now let's create a particle-antiparticle pair. This would mean that we now put, when it comes to occupation, would have an occupation of 1 here. That would mean now that there's an electron. And we would put, looking here, like make the occupation 0, and now also have a positron sitting here. So now
we have a question.
Yeah, please.
This Stagger fermion configuration looks like it is equivalent to an antiferromagnetic configuration. There is a connection between the two.
Yes, in some way, in some cases, yes. That say there is a model which I will describe later on. I will not get into these details because of time is running. The quantum link model, there can be symmetry broken phases in the quantum link model, which exactly relate to an antiferromagnetic ordering of these occupations. So where this is not really nailed, this may be more like charge density wave here, but where you can have a symmetry breaking, like as you would have for a charge density wave. Like this configuration plus like the symmetry conjugated partner would be the degenerate ground states of a gauge theory. This can happen, but it's not generic, not in everyone. It can happen.
Okay, thank you.
Okay, now let's do just physics. So we create now like an electron-positron pair. Now we have charges in our system. Before we didn't have charges. So now, since these two charges are separated by some distance, and the distance is in the end like the lattice spacing here, that's a dipole, right? We have generated a dipole, minus charge and plus charge. So this is just, we have created a dipole. Now, from dipoles in one dimension are now special. So if this were a dipole like in 2D or 3D, we would like draw some electric field lines which like connect like the positive with the negative charge, right? But in one dimension, there is no field line that can like go up here, right? That's just not allowed. So we cannot have lines that take this way. But what we can have, of course, is that there is a field line directly on a one-dimensional line which goes that way. further, we know one thing, that there is, when you look at the dipole and the electric field generated by a dipole, that there is no electric field outside of the dipole along the dipole axis here. So which means that out here, there is no electric field contribution from the dipole. If we generate now one of these dipoles out of the vacuum, it means that also, like, after creating the dipole, there will be a vanishing electric field outside of the dipole. Yeah? Cannot be else. So as compared to the previous configuration, when looking here, say, where we had outside, like, also like vanishing electric field, now we have an electric field inside connecting the dipole, and we have now the two charges sitting at the two lattice sides. So what that tells us is that, like, that's a manifestation, like that the charge and the gauge degrees of freedom are, like, not independent of each other. They are connected. If I generate charges, I have to adapt also, like, the corresponding electric field. Like, that's what we know from QED. And that's how charge and electric and the gauge degree of freedoms are mutually intertwined. Right? And all of this can be captured in the end by Gauss' law, which tells us that, like, in general language, like from electrodynamics, that's what Gauss' law is like. On the lattice, of course, we would have to replace this divergence by a discrete one, which means, like, we look at a difference of two electric fields, and this will be just the charge density of matter fields at a given level. So in the end, this would correspond, say, to that electric field, this one here to that one, and this would be the corresponding charge here, right?
Just one question from the chat by Satoshi. When you say there can't be any field after 0 and 1, is it also true for periodic boundary conditions?
Yes, there's no reason, like, for no constraint a priori on the boundary conditions. There are some theories which are better formulated with open ones, but in general, there's no particular reason for going for one or the other. You can choose, like, for your application or a concrete calculation, what is more appropriate for you, mostly. Okay.
Okay,
so,
there's one more question by Artem.
Yes, so my question was a bit, it seems that kind of everything is sort of short-ranged here, because, I mean, in principle, should I not have a field anywhere, even if I have a single charge? Or if I have a dipole, then it will decay, like with some power law?
Okay, right. But that's like, so, like, that's because a dipole in one dimension is special.
Oh, okay.
If we were in two dimensions, say if we would have further lattice sides here, say, then things are different, because then we can have also, like, an electric field, say, contribution, which, like, into the second dimension. Like, there can be electric field lines which go in the second dimension, but in one dimension, that's not possible. And the only thing that remains then is that there can be an electric field contribution here in the center. That's very special in 1D.
Okay.
But if you put, like, what would be very different if I were just to put one single electron in the system. So if I were just to put a single electron somewhere in our system, so, like, let's say here E minus, and we would have a vanishing electric field here, we would have, or, like, we can visualize this as, like, putting the other part of the dipole, the positron, very far away, we would have to change the electric field on every link here. So that would be a macroscopic change of the electric field configuration by adding one electron hole pair, or like one electron positron pair. So that is a rather, it's not really non-local, but like a long range kind of change of the configuration here, which comes because of Gauss law, because you always have to satisfy Gauss law. Yeah, so as expected, I'm running out of time. So I would maybe now just I will skip now a detail, like I will just now mention, for the sake of simplicity, a particular class of models which are very convenient for the study of this disorder field localization or gauge theories, and this class of model goes under the name of quantum link models. And you can find, for instance, a nice summary in Wiese in Annals of Physics from the year 2013. And so like that's now the first time I will write down an actual Hamiltonian. So, and the Hamiltonian has 3 parts. It has one part which you know very well. So like that's E is the electric field on a link. EL is the electric field on a link next to a lattice side L. And that's the usual E squared term that you know from electrodynamics to the energy, right? Then we have also like a mass term for our matter fields, for the electrons, say, and the positrons. And because of this staggering, there will be also a staggering here in this mass term. Okay? And now third comes the important term, which is then in the end describing the coupling between the matter and the gauge degrees of freedom. And this is a term which has the following very generic structure. This is a hopping of like an excitation, which can only happen upon, or with this hopping being coupled to some operator U. And the that is also like in the end related to the gauge degrees of freedom. And for these quantum link models, what we have is that we represent the gauge degrees of freedom by spins, not bosons, but by spins, where the electric field will be as simple as Z operator, and the ULs will be ladder operators. And if you take that Hamiltonian, you can convince yourself that if you define these operators GL as like in the following way, where this here is nothing else than the charge density, and this here is the gradient of the electric field. So like that's GL is nothing else than an operator version of Gauss law. Then you can convince yourself that these GLs commute with the Hamiltonian and also commute mutually with each other. So we have here one example of a abelian lattice gauge theory.
Okay, Anton, you can ask your question.
Yes.
First of all, could you please specify whether there is any constraint on the spin quantum number? I mean, is it spin 1/2 or anything else?
You can choose whatever you would like, or like what.
Okay, makes sense. And secondly, could you please also comment on why spins cannot hop on its own? I mean, the last term represents hopping term, which involves kind of vector potential part, but
Exactly.
I would also expect something like a pair hopping. I mean, if I remove completely the electromagnetic sector, I would still expect that the fermions can move on their own, and this Hamiltonian suggests that they actually cannot. I mean, after I have only bare electronic part, I can then insert electromagnetic part by means of gauge invariance and obtain the kind of term you've just written at the third one. But I still wonder how is that fermions cannot move on their own?
Okay, because actually the motion here is actually not really motion. Like this hopping here is actually not motion. What this does is it's like in terms of this mapping here. So if say this particle moves from here to there, physically speaking, that's actually related to the creation of an electron-positron pair. So the propagation of actual particles, electrons and positrons, is effectively generated by fluctuating electron-positron pairs, and like it's a big soup. And this big soup allows you to transport electrons and positrons, but only indirectly. So I know that not directly answers your question. So you have been somewhat wondering what happens if, or is there a limit where I can eliminate, say, my gauge degrees of freedom and get a simple hopping Hamiltonian? And the answer is, I would say no. That's a different model.
Okay, so is there, this is precisely what I'm asking now, is there any, let's say, is there any certain motivation behind that, or is it just a choice of the model which is like simple to analyze and etc. etc.?
So it's actually a rather so upon, let me say it that way, like if you specify certain symmetries that your gauge symmetry should have, like a global U1 symmetry, the number of these psi excitations is conserved, say. And if you require that your gauge degrees of freedom, like not bosons, but rather like finite dimensional, then this is the gauge theory, the minimal gauge theory that you get, compatible with these symmetries. You don't have so many choices upon specifying symmetries.
Because I'm still trying to figure out how I can manufacture a theory with a hopping, something like a little bit more intuitive at this point, yeah? But probably let's postpone this discussion because it looks like you have a shortage of time, so yeah.
No worries, no worries. So the point is what this term is somewhat like taking care of is that, so like when you move around excitations, that you always have to make sure that you appropriately modify always the electric field.
Yeah, this I understand.
Essentially, if you move a charged particle, also the electric field lines have to are following your particles. And that's what this term is doing. And you don't have a choice for this term. This term is fixed. by
sure, it's fixed by gauge invariance. That's for sure. This I can believe easily. Yeah, that's fine.
Like, this does not mean that you can add further terms. So that's like the minimal Hamiltonian that you can write down. For instance, I could also write down an e to the 4th term in principle. Like, that would be something which is okay with all the symmetries, and maybe there are certain physical realizations where this is a necessary term. Yeah, you can do a lot here, but like, that's the simplest version. Say the bare one. You can add things to it, but like, that's the minimal model.
Okay, there is also a question by Edith. Can you map in the lattice the terms G, M, and K for more understanding?
Can you say the question again?
Can you map in the lattice the terms G, M, and K for more understanding?
Not sure I understand the question.
I guess maybe to map it to some concrete model.
Yeah.
It's what are the physical parameters of
so
if you would look at electrons.
Okay.
Edith, you can also take, you can also talk if you want.
So I think that, I don't know whether there's an easy answer to this question, because
okay. In the lattice, you have George field on bosons or spin that you present. I want to know if J is interaction into George field with lattice field. If you want to represent the term of your Hamiltonian in the lattice.
I'm not sure I got the question. Are you asking about a continuum limit and lattice?
No. You write an Hamiltonian, and you have 3 terms. I want I want to understand this term in the lattice occupation that you represent up in the
Okay. Let's maybe do that. Let's take one. Okay. And let's put it here for a second. Okay. So
yes.
That's, I think, what you were asking for.
Yes.
Okay. So this E squared term counts like the electric field strength on the link. And the electric field strength here is given by a spin. So meaning that if we are in a spin, if we take a spin one half would be trivial, because then Z squared is 1 and this term does not play a role. But if you say that this is a spin 1, the LZ could have like 3 different values it takes: -1, 0, and 1. And you would, like, this term would imply that like the -1 and 1 eigenvalues contribute an energy, the 0 does not contribute an energy here. This is the mass term, so it gives us, like, tells us when there is an electron or positron with a certain mass m. These are these occupations here. And then this one here is like moving, say, this particle from that lattice side to that lattice side by changing appropriately the electric field on the link, so that you always respect the local symmetry. Namely, that this GL commutes with the Hamiltonian.
Okay, thank you. I understand now.
Good. As you can see, I'm embarrassingly running out of time, but that's good. There were many questions. I like that a lot. So I will now just, in the last, say, 5 minutes, I don't want to take more of your time, go to the actual topic of my lecture, but I think I can still convey the message. I hope so, at least, which is disorder-free localization. Good. So what I would like to do now is, so we had from gauge symmetry, we had this property that the Hamiltonian decomposes into these blocks, right? Where each of these blocks were like determined by the super selection sector with these charges Q alpha, which were the eigenvalues of these generators GL of the unitary of the local gauge transformation. So up to now, so what I now want to do is that I want to give these QLs, which were just numbers here, like eigenvalues, I want to give them now a physical meaning. And that's actually very simple if you consider like something like the quantum link model or some kind of simple form of QED, where these generators GL in the end are Gauss law, divergence of electric field and the charges. So now let's just actually use that property and replace the left-hand side, the GL, actually by Gauss law. And let's bring the right-hand side here, like the left one. What we will find is that we can reformulate the condition for, or the definition of a super selection sector in this form, right? I've done just a simple rewriting of things. But now you can see that the QLs appear on the same level as the charge density rho L, right? So in the end, these are static because they cannot move. Like as these charges here, they can in principle move around and can be created and destroyed, electrons and positrons. But here we have some other kind of charges now, which are static. And the main implication of this is that one can say that a super selection sector is, or choosing a super selection sector means like choosing a sector with a certain static background configuration, background charge configuration. So choosing a random super selection sector, so meaning in the end choosing somewhat random number QL, means that you choose a configuration of random background charges in your system which are static. And that this can generate effectively kind of disorder is somewhat natural, I guess, and at least intuitive. And that's where what this disorder-free localization is about, like that choosing a random sector, or the question whether this can lead to localization. And I think for the moment, I'll stop here because I'm already over time. And so at least I had the chance to pose the main question here. And it turns out actually that this is possible, that a random sector that there are random sectors which can be localized. And however, key aspect is that the gauge theory itself, there is no disorder. Like the gauge theory itself, like this quantum link model here, that's a purely homogeneous Hamiltonian. There's no inhomogeneity in that Hamiltonian, right? Just by choosing like a super selection sector, you can make the system localizing, although the Hamiltonian itself is purely homogeneous. And the reason is that there are these constants of motion. The constants of motion are defining your super selection sector, and these define your random background charges. And that, in the end, for some models can lead to localization. But with this, I would like to stop. I have some more material, like on my notes, that I will share with you. But for the moment, I have to stop here because of time. And thanks a lot for asking so many questions and for your attention. And if there are more questions.
Yes, there are 2 more questions. So thank you, Markus. Artem?
Yes. So, I mean, I understand this is very brief, but at the end to this order free localization part, I mean, it feels a bit like you're mixing operators and just scalars here, no? I mean, these QLs, you said that they are charges, but they're not even operators, they're just scalars. I mean, I don't quite understand. I mean, the statement is, I would say, pretty much trivial in some sense, like it's just a quantum number, and you're saying that that's the eigenvalue of the wave function. No, I mean,
no, I'm trying to give what I'm trying to say is like to give them a physical meaning. So what I wanted to say is like choosing a random super selection sector is choosing, like, say, randomly these numbers QL. But you can think of these numbers QL as like, or choosing them somewhat like that that you choose a set of static background charges, right? Which your electric field, say, has to adapt appropriately.
What I mean, these QLs, they do not appear in your Hamiltonian, no? There's no Hamiltonian term that includes them. They're just, as you said, they're just scalars.
Yes, right. But, and that's like the subtle term, and which I was not able to actually consider here, they don't appear in the Hamiltonian, that's correct. But they are extremely important for the dynamics because Gauss' law connects or constrains the allowed electric field configuration, say, given a certain charge configuration. So Gauss' law tells you that although the background charges are not appearing in the Hamiltonian, when you put them initially in your system, in your initial state, they will significantly affect your dynamics. That's where conservation laws in the end enter. Yeah.
Yeah, I guess, but I mean, I guess that's just an effect of this local conservation laws that you have. No, so this is just a reformulation, but I just mean the naming of this order free localization. I mean, these are just local conservation laws that are conserved.
Yes, you can also think of it just as like some local conservation laws. What I'm telling you here is that you can also think of them in the quantum electrodynamics language when you have a theory of quantum electrodynamics. That these are really, you can think of them as electric charges that you put there.
Yeah.
And now if you have electrons or positrons moving in a system where there are already many, say, other charges randomly present, and they can generate like a background, like an effective disorder potential in the end. And then the argument is, of course, this very much resembles the usual scenario of localization. that you have charges moving in a random potential, and then you can get localization.
Okay.
Maybe can I just rephrase at some point if it helps? So if you're looking in a certain manifold of a solution with QLs, it means if these are just your quantum state, it might help to consider these QLs and interpret them as charges.
Yes.
Is it that what you?
Exactly. And so you can, of course, view them as abstract objects, and this will not change the overall result finally that you can get non-ergodic behavior. But what I'm telling you here is like just an argument, also for the sake of time, that you can give them a physical meaning, and you can maybe already anticipate at that point that a random superselection sector in the end generates a random background charge configuration, and moving in the random background charge configuration can lead to localization in the end. Yeah, that's just like the physical picture, but you don't have to take that physical picture. You can also stick to the formal one and just interpret things along these lines. That's perfectly fine too.
Okay. So I think there is another question.
Yes, I wanted to ask.
Okay.
So I have actually two questions. So the first one is that the rho L, these are the lattice side charges that we are like in microscopically putting, right? Like the zeros and like electrons and positrons. And so the QLs, that these are like emerging sort of after like an effective charge that is emerging from the model, I guess.
These are like, so upon choosing a super selection sector, you're artificially, or not artificially, choosing a super selection sector means that you add some further, like,
discharge.
Let me do a quick example, because that's actually what I wanted to do also. Like, let me try to do that quickly. I think that hopefully clarifies these questions. So let's again consider, say, here the case. So where we have like 3 lattice sites, and we have now dynamical charges like a positron, an electron, and wait a second, and sorry. No, that's like wrong. That's like no positron. Now you can think of having another channel here, which are these QLs, and which I can put here. I can also put like an electron, say, on a site where like otherwise only positrons live, and put another particle here, and I can say there's maybe no electron here. And so what that means is, like, depending on, even when I fix my actual dynamical charges here, the allowed electric field configurations are now constrained by these artificial charges that I can put side by side to the dynamical ones. Like in this case, for instance, we would have like, we could have a vanishing electric field in this problem, although we have dynamical charges, but we compensate them always by static ones, say. So you can have, so like that's one effect that you might see, like in higher dimensions at least, that say like the dynamical charges would like to screen the static ones and compensate.
Yes. Okay. Okay, I understand. And the second question was that, so you are saying that because there are like super selection sectors corresponding to various values of QLs, and this randomness can generate a localization in the system. But my question was that they are not at all related, right? Because of the abelian nature of the theory. So if they are not related, how will one QL affect another QL, which in turn will generate localization? I mean, it seemed to me that if the theory is non-abelian, then only can this randomness in charge sector can generate localization. I don't know.
You mean the case you're asking for the non-abelian case?
No. So you said that okay. So you said that this is, so what we have done, what you had done till now is an abelian theory, right? And you have these sectors in the Hilbert space which corresponds to different values of QL, and then you said that this random sector can generate localization.
Yes.
So my point is that like two different sectors, they don't communicate with each other in any way, right? Because they're abelian. So how can this randomness generate localization if they don't talk to each other? That's my question. Like, okay, if I'm not sure if I understand, like if I told the question correctly.
So now let me try to answer it the following way. So if we choose a certain background charge configuration, that means we choose one of these sectors here, say. If we start from, so like some initial condition, which just lives here, we would only have dynamics in this block. Right? Now, you will never, of course, jump like to these other blocks. Everything would take place just inside of this block.
Right.
Now, inside of this block, let's maybe take another Fourier representation. You would have now, say, various like charges like that sit here, and now you have, say, an incoming particle that wants to like propagate through this medium of background charges. And now, like this electron, say, will of course be scattered, right? And now the point is that if there are sufficiently many of these scatterers, it can happen that you get localized.
Okay. Now now, yeah, this physical picture. Okay, yeah, now I understand. Okay.
That's the main idea behind this.
Okay. Thank you. Yeah, now I understand. Okay, thank you. Thanks.
Okay, so thank you, Markus. Okay, maybe we can, Markus, maybe
there's one more question. No,
there is one more question.
Please.
Yeah, I had the same question that I was asking about this gauge theory and the projection thing. So if I understand this correctly, so when you do projection mathematically, what you essentially do is you construct some kind of a differential operator on the manifold and look at its kernel, and that is your gauge fixing. So is that connected to this choice of QL, and is that the gauge fixing we are doing here in this?
Yeah. So good that you ask. I think it was you who was already asking about this before, and I forgot. Now, thanks that you ask again. Now, I think what you're somewhat like have in mind is what is like the case such as you have in high energy physics, where there is a natural super selection sector to consider, which is namely the one of zero background charge.
Right. Exactly.
And so this means that in such a case, of course, there's no it doesn't make sense to talk about this disorder free localization in the end, because you will not have any background charges. But there are many other incarnations of like gauge theories, which like in condensed matter physics, where actually, say, when you think about quantum spin ice, say, I don't know whether you're familiar with that, or quantum dimer models, that's actually rather natural to add or to think in experimental realizations to think about these background charges being present.
Right.
Just due to imperfections. And like then this would imply that you're working in a different super selection sector.
Right.
So it comes from like, it depends on like how you, from your background. I think from high energy physics point of view, this does not make a lot of sense. Because you
so
always
essentially
have a single super selection sector to consider.
Yeah, so essentially, like choosing your fixing your QL, fixes a super selection sector. So is that kind of equivalent to a choice of gauge? I mean, not essentially. I mean, okay, in high energy sense, you will never have I mean, the same theory because your charges affect your physics. This free charges, static charges. So usually gauge. I mean, what I was asking essentially was, usually gauge theory comes with an underlying degree of freedom, where which you can mod out, and for the classic example is in QED, if you like in not QED, like classical electrodynamics, you can choose any gauge and that will still give you the same physics. Like there is a degree of freedom, gauge degree of freedom. So I was trying to understand the analogy here. Yeah.
Okay, I think so like say like you're asking somewhat so you have in mind like say choosing Landau or like what other kind of gauge for like
Coulomb
for
gauge,
representing your
yes, you can.
okay.
Yeah.
This does also like so like that's a kind of like, of course it's very much related, but in the end no matter which kind of gauge you use in that sense, like to represent your Hamiltonian, the local gauge symmetry will always be there.
I see. Okay.
It doesn't depend on how you represent like the Hamiltonian for your dynamics, say. Like there you have different choices. You can there's like you can choose the gauge that you would like to. The local symmetry does not change under that.
Okay. Cool. Thanks.
Okay. Although what changes is really the Hamiltonian. So what I mean by that is like choosing different gauges for your electric field. These are not unitary transformations, like going from one gauge to the other.
Right.
Which means that in the end, you change the Hamiltonian, but the local symmetry should be of course identical. Gauss law always has to hold. There's nothing you can do around that. Yeah?
Cool. Thanks.
Welcome.
Okay. So thank you very much, Markus. So I think it's time to have a break, at least a break of 10 minutes. So we'll start again at 11, and we will start with Marco. Okay.